Stability of a carbocation depends on inductive effect, hyperconjugation or resonance. Out of these, resonance is the dominating factor, then comes hyperconjugation if resonance is not present. If hyperconjugation is also not present, we will see positive inductive effect. More is positive inductive effect, more will be stability. We have taken an example over here where you can see we have three alkyl groups, here we have two alkyl groups, and here we have only one alkyl group, and alkyl groups have plus I effect. So here we have plus I from three sides, plus I, this shows plus I and this shows plus I. So positive charge decreases significantly. So this is more stable. Here you have two alkyl groups. So plus I is less plus I, so less stable. Here one alkyl group is present, so it shows very less positive inductive effect. So more is inductive effect, less will be charge and more is stability. So stability order is like this. This is a 3-degree carbocation, this is 2-degree and this is 1-degree. And if alpha hydrogens are also present, then what will be the reason? We will say hyperconjugation, not inductive. Alright. So hyperconjugation is a dominating factor, and if it is not present, then we will say about inductive. Alright. So this is stability order 3-degree, then 2-degree, then 1-degree. Alright. Next is you have rearrangement of carbocations. Rearrangement occurs whenever carbocation is formed. For example, if you are having a SN1 reaction, then rearrangement of a less stable carbocation occurs to form a more stable carbocation. So what could be the phenomena? There could be hydride shift or a methyl shift or ring expansion or ring contraction, and the sole purpose of these arrangements is to form a stable carbocation. So what is hydride shift and methyl shift? I'll explain it to you over here. If we have something like this, CH3, CH2, CH2 plus, what happens is hydride shift is the possibility over here, and it always occurs from the adjacent position. Here, if we have this carbocation, this can rearrange by hydride shift to form a more stable carbocation. This is a 1-degree carbocation, and the number of alpha H over here is 2, and this rearranges to form this carbocation CH3 CH plus CH3. So the number of alpha H over here is 6 alpha hydrogen and 2, this is a 2-degree. So more is number of alpha hydrogen, more is the stability. So this gets rearranged to form this one, and the phenomena happening is hydride shift. What exactly happens? I'll show it to you over here. We have, what we see is whether this has a hydrogen, this will break like this, H minus, and the carbon backwards gets a positive charge. This H minus shifts to this carbon. So this H minus goes to this carbon plus, H minus and carbon plus forms a CH bond. So instead of CH2, it becomes CH3, and the back carbon gets a positive, and this is more stable. So this is the rearrangement due to hydride shift. Similarly, if hydrogen is not present, then methyl shift happens. Let me show you with another example. If we have something like this, where there is no hydrogen over here. So what will happen is this will break like this, where you will get minus over here and the back carbon will get a plus, and this negative carbon goes and attaches to this carbon. So what forms over here is something like this, CH3, C plus, CH3 plus, and you have CH2 getting attached to a CH3. So that is what it had. Alpha H, how many alpha H were there? 0 alpha H here, and here you can count 3 plus 3 plus 2, overall 8 alpha hydrogen. So this is more stable. So this gets formed by methyl shift. So this one was hydride shift, this is methyl shift, and the sole purpose of all these rearrangements is to get a more stable carbocation. So more stable is the carbocation, more will be the reactivity, and the product formed in a major quantity is the product formed through a more stable carbocation. So that is for now. Thank you.